I'm now going to go over the answers to the second test. Now, of course, I've already put up the answers, so you should have looked at them, and right now you should have them in front of you, either on a screen or printed out, because I'm going to refer to these without necessarily rewriting the problem. All right, let's look at the first recurrence. F of n is f of n minus 3 plus 3 log n. Now this one is actually fairly simple. You use the antiderivative method. Subtract f of n minus 3 from both sides. And this, of course, gets rid of this term on the right side and creates this on the left. Then divide both sides by 3. That cancels this 3. But on the left side, this is a formula for an approximation of the derivative of f. Now, it's not exactly equal to the derivative of f, but we don't really care because we're doing asymptotics. So f prime of n is then theta of, it's not exactly equal to that, but we don't care. It's theta of log n. You see that? Which means that taking the antiderivative, f of n is theta of, now the antiderivative of log n is n log n minus n, but we don't care about the second part because we're doing asymptotics. So the correct answer is theta n log n. All right, now let's look at the second problem here, which is considerably harder. We're going to do a substitution here. F of n is the f of the square root of n plus 1. Now, I told you what to do. Let n equal base 2 logarithm of n. And so, therefore, we want g of m to be f of n. But recalling this, since m is the base 2 logarithm of n, well, perhaps I should write this in opposite order. F of n, which is here, we want to be equal to g of m. So this equation here is the definition of g. But now we're going to write this as g of the base 2 logarithm of n. All right, so now the next question is, what is f of the square root of n? Well, that's going to be g of the base 2 logarithm of the square root of n. But the logarithm of the square root, you know the square root of n is n to the power of 1/2. So using the usual rule of logarithms, we multiply their logarithm by that new exponent, which is 1/2. So therefore this is g of log base 2 of n divided by 2. Using the rule that this square root of n is equal to n to the power of 1/2. Now, we rewrite the whole thing in terms of g. So f of n is g of m. F of the square root of n is g of, and then base 2 logarithm of n is m. So this is m over 2. And the 1 doesn't change. Now the master theorem tells us the answer. The answer is that g of m is theta of m. G of m is, theta of log m. Oh, I run out of space. So g of m equals theta of log n. All right, now remember that f of n equals g of m, and log m is n. Log n is m is the log n. So we get log n. There we go. Sorry about stumbling. Okay, let's continue to look at these problems. We have this one. Now, these 2 and 3 are not the same number, so we have to use the generalized master theorem. And remember that n is n to the power of 1. So we ask ourselves the question, what's 1/2 to the 1 plus 1/3 to the power of 1? Well, that's clearly 1/2 plus 1/3, which is 5/6. So therefore, this number is less than 1. Now, according to our rule, if that sum is less than that power here, so we have 1/2 plus, let's see, where did this go here? 1/2 plus 1/3 is equal to 5/6, which is less than 1, which means that we take this power and that's the answer. F of n is theta of n by the generalized master theorem. All right, let's go over to this one here. This particular problem is another difficult one where I told you the substitution. It's sort of the opposite substitution. In the previous problem, we had m equals base 2 log n. Now we're doing it the opposite direction. M is 2 to the power of n. But we also still want g of m to equal f of n. All right, now since m is 2 to the n, that's the same as g of 2 to the m, 2 to the n. So what's f of n minus 1? We use this formula here to say that's g of 2 to the n minus 1. But what does it mean to say g of 2 to the n minus 1? You know that when you add powers, you multiply the exponents. No, I'm sorry, you multiply the powers when you add the exponents. So that means that this is g of 2 to the n times 1/2. And g of 2 to the n is in fact equal to m, so this is g of m over 2. All right, now translating up here, f of n is 2 times f of n minus 1, so we could write g of m is less than or equal to 2 times g of m over 2 plus 1. All right, now, according to the master theorem, we know the answer to that. Well, first of all, f of n is the same as g of m. And by the master theorem, this is not theta, but O. O of m by the master theorem. Now, m is 2 to the n. So that means this is O of 2 to the n, and that's the answer we are looking for here. All right, the next problem we have f of n is greater than or equal to 4 f of n over 2. Ah, look what I forgot to put. I forgot to put the f here. Oh well, you knew what I meant, right? All right, now, this is a master theorem situation, and we know that 4 times 1/2 to the 1 is 2, which is greater than 1. So basically what the situation is, according to the master theorem, is that f of n is omega, why? Because that's greater than or equal to n to the power of the log base 2 of 4. Now, I don't expect you guys to know the base everything logarithm of everything. Of course, if you have a calculator, you can approximate it. But you should know that the base 2 logarithm of 4 is 2. So 2 squared is 4, which is the same as saying the base 2 logarithm of 4 equals 2. And so this is omega of n squared. That's the answer. All right, let's go to the next problem, which is this one here. Now, here I have f of n is f of n minus square root of n. Now, square root of n is a lot smaller than n, and so this is like antiderivative. We move it over to the other side, and then we divide both sides by the square root of n. All right, now this is in the form of f prime, because square root of n is close enough to 0 to make that approximately f prime of n. So that means that f prime of n is approximately equal to, well, it's theta of, and then n divided by the square root of n is the square root of n, which, as you know, is n to the power of 1/2. What's the antiderivative of n to the 1/2? You should know that it's n to the 3/2 divided by 3/2 from calculus. Well, we don't care about the 3/2 because we're doing asymptotics. So the answer is theta of n to the power of 3/2. And that's the answer. All right, here we have a problem with the generalized master theorem. And we're trying to find a constant k such that the solution of this is theta of n squared log n. Now, if we look at our master theorem, we can set it up this way. Now, there are only two terms. There could be more. Alpha 1 times beta 1 of n plus alpha 2 f of beta 2n plus n to the power of c. c is 2. And so what we do is we take alpha 1 beta 1 to the c plus alpha 2 beta 2 to the c, and we ask the question, is this equal to 1 or less than 1 or greater than 1? If it's less than 1, the answer is theta of n to the c. If it's equal to 1, the theta of n to the c log n, which is what we want. If it's greater than 1, the answer is more complicated. I'll put that on the other board. But if we apply this here, we get 3/5 squared plus k times 1/5 squared, and we want this answer, n squared log n. So we want this to be 1. All right, now, with old ordinary arithmetic, you can now figure that this is 9/5 plus k/5 equals, no, 9/25 plus k/25 equals 25/25, which is 1. And so the answer is clearly k equals 16. All right, now I told you I would remind you of what the answer is in this other case. That answer is obtained by asking this following question. Find, all right, now this is the case that alpha 1 beta 1 to the power of c plus alpha 2 beta 2 to the power of c is less than 1. So what you do is you want to find, it turns out the value of c is irrelevant to the answer. No matter what c is, you get the same answer. So you want to find an exponent, we'll call it k, such that alpha 1 beta 1 to the k plus alpha 2 beta 2 to the k equals 1. And then the answer is theta of n to the power of k. That's the solution in that case.
1.
Now, this next problem involves log star. I actually told you that if I use this, then the answer is log star. You should simply memorize that. However, it actually can be worked out using information you know. Let's look at the definition of log star. First of all, we're going to use log base 2. Let's assume our calculator has a button for log base 2. And what we do is we say, put in the number x, and then press that button until you get a number that is no more than 2. No more than 1, I mean, less than or equal to 1. And when you get to that, you stop. And the number of times you push the button is log star of x. All right, so how would we do this? Log star of x, well, if you're already there, it's 0, because if it's less than or equal to 1. But if it's more than 1, you're going to have to push the button at least once. So that one time you push the button is there, and then you're going to evaluate the log star on the remaining answer, what's still left in the calculator. So this is actually the definition of log star. All right, now, let's see how that works. We can actually do something with that. So we'll say, let j equal log star I. And so then we have for j equals what? Log star n, because the initial value of I is n, and j is log star of that, so it's log star n. All right, and now what are we going to do? We're going to say that j has to be greater than 1. And then j goes down, j equals j minus 1, because we're decreasing it every time. And how is that possible? Because when I say I replace I by log base 2i, I use this formula to indicate that the value of j, which is log star I, decreases by 1 whenever I take the log. All right, so this is, of course, log star. So now, let's solve this one. J equals log star n.
Fine.
All right, so that's the initial value. Well, try to think of it this way. We're decreasing j by 1 every time. If we start with this value, how many times do we have to decrease it before it reaches 0? Well, actually 1. So I guess this should be 0 here. And the number of times we have to decrease it is equal to that first number here, which is log star n. So the answer is theta of log star n. And this calculation doesn't use anything you didn't already know.